we're going to look at these subsets. And so we're going to start from the smallest subset possible, and that's natural numbers. So what are some examples of some natural numbers? Examples of natural numbers. 1. Okay? Natural numbers are actual counting numbers, but not 0. Anything positive. So 1, 2, 3, dot, 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 up to infinity. Okay? Who can tell me the difference between a whole number and a natural number? Not negative or decimal is a whole number. That's right. So the only difference between wholes and natural, it includes all the natural numbers, and in addition to that, you have a 0. So whole numbers are 0, 1, 2, 3, on to infinity. Integers. What's the difference between integers and whole? What are we adding to the integer set that the wholes don't have? Not fractions and decimals. That comes up next. Negatives. Yep. So we're going to have dot, 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 like -3, -2, -1. Okay? So all those get added to what's already whole and natural, because those are all part of integers. Yep. 0's inside of that box. Okay, now we're going to talk about rationals. What's the difference between rationals and integers? What do we have? We have decimals. Specifically, we have terminating decimals, so like 0.625. It stops. We have repeating decimals, so like 0.3333. If it's repeating, that's a rational. And we have any fraction that you can make, so like 5/6. Okay? So a rational number is any number that can be made into a fraction. And then yesterday and the day before, we were talking about irrationals, which are those crazy numbers that go on forever with no rhyme or reason. They have no terminating decimal. And they have no repeating decimals. So, like pi, square root of 2, those are all irrationals. And all these come under the envelope or the umbrella of real numbers. These are all part of the real number family. Can you give me an example of a number that is not a real number? Actually, I would say that's a good guess. Infinity was brought up, but I think that's actually a real number. Huh? Imaginary numbers. Okay? So, imaginary numbers are not part of the real number family. You've never seen them?
No, I haven't, and they're probably the same.
Okay. Okay, so let's take the number -9. What does that belong to? Does it belong to natural numbers?
No.
Where does it belong? Integers. It belongs here. Where else does it belong? Oh, yep, it's a rational number. And it's also a real number. So -9 could be any of those. How about -1.3? It's rational. What else is it? It's real. Okay. How about 0? It's a whole number. It's an integer. It's rational. And it's real. How about 0.33333 repeating? Nope, it's not irrational. It's rational, actually. It's a repeating decimal. And it's real. Okay, how about pi over 2? Yeah, that is irrational. And it's real. Okay, how about square root of 9? It is an integer. It is real. Yes. It belongs to everything but the irrational group, right? How about square root of 10? It is irrational. And real. There's these two little properties called closure for addition and multiplication. And basically it's just saying that if you take two real numbers and you add them together, you still get a real number. Okay? So you can even rewrite it as a real plus a real equals a real. Okay? The same is said with multiplication. A real times a real is still a real number. So if I have 3 plus the square root of 2, because those are both real numbers, that still ends up being a real number. Okay? If I multiply two different, if I take pi times 3, it's still a real number. So I wanted to talk about these being closed. What is closed under multiplication? It says our natural numbers closed under multiplication. So in other words, if I take any natural number and multiply it to another natural number, does it stay a natural number? So give me some examples of natural numbers. 2 times what? 3. 6. Is that a natural number? Yeah. Can you find any natural number that this wouldn't work for? So yes, it is closed under multiplication. Okay? The next question is, are the integers closed with respect to division? No, why not? So yeah, so like if I take 4 divided by 2, that's still an integer, right? So that one works, but give me an example where it doesn't work. Yep, 6 divided by 7. It's going to be a decimal of some kind, right? So this is not closed. So the outcome of 6 divided by 7 is not an integer. Commutative property of addition. So all this is saying is that you can take two numbers and add them together one way. So say like 3 and 4. And that's 7. And that's the same as being 4 plus 3, which is still 7. It doesn't change, the order doesn't matter when you're adding them together. Okay? The one thing you should think about when you're thinking about commutative is think about the base word in commutative, which is what? Commute. And we use that every day here in the metro area because a lot of people commute to work. What does it mean? Yeah, we're traveling or moving, right? So the only thing that changes here is that the 3 and 4 are traveling or trading places. So when you're looking for a commutative property, you're looking for when it changes places. The same is true for multiplication. So if I have 3 times 4, That's the same as saying 4 times 3. They just traded places. The outcome is still the same. Okay, so associative property is just basically saying that these numbers are not trading places, they're not moving, but the only thing that changes is who they are grouped with. So if you look at this first one, B is hanging out with A. It's grouped with A. But on the second one, B is with C instead. So you can really think of the base word in associative as associate, and which numbers are associating with which numbers. Okay? So if I did this, 1 plus 2 plus 3 is the same as saying 1 plus parentheses 2 plus 3. So on this first one, 2 is hanging out with 1. And on the second one, 2 is hanging out with 3. That is true also if you're doing the same thing with multiplication. The same rule applies. So it's all based on which number associates with which number. The last one today is distributive property. It's always taking the first number on the outside of the parentheses and making sure everything on the inside gets that number. Okay? I think about my children. I have 4. If I bring home a candy bar and I don't give them each a candy bar, what do you think is going to happen? Yeah, a riot will happen for sure. So you can think of it as A is the candy bar and B and C better get each of them get an A. Okay? One of the things that I wanted to talk about a little bit is what happens when you have a square root involved in distribution. So if I have like this, 5, 6 plus square root of 2, and I have to distribute that 5. Well, it's going to be the same thing as saying 5 times 6 plus 5 times square root of 2, which just happens to be 30 plus 5 square root of 2. So you're going to follow the same rules that you would do anyway with square roots. Yes. Which associative one is it? Multiplication. Okay. How about the next one? No. It's not distributive either.
It's the one where it doesn't matter what order.
Right, what is that? Commute, because really the square root of 5 and 4 are trading places, right? The 3 didn't get distributed. The 3 is still on the outside. So what we're seeing here is commutative with addition. Okay?
Distributive.
Yes, the next one is distributive. That 3 got transferred to both the square root of 5 and 4. Okay? How about this next one? This one's a little tricky. Yeah, it is. It's commutative. Of what kind? Not addition. Mult. Yeah, multiplication, because really 2 is being multiplied to both of these. It didn't get distributed, it just traded places. Okay? So, I just want to point out that B and D are kind of tricky. Okay? Just make sure you think about if things are moving or changing associations. Okay?